Hi, I'm Antti, and this talk is on our paper Polylog Competitive Deterministic Local Routing and Scheduling, which is joint work with Bernard Hauptler, Sharmal Patel, Clifford Stein, and Goran Zizek. So, in this paper, we solved a routing table problem for packet routing deterministically. What is packet routing? Well, in it you are given an undirected graph, and there are some packets in the graph. Each packet has a start and a destination vertex. So here we have one from A to D and one from B to D. Then there are multiple time steps, and each time step, each vertex can send some of the packets on it to adjacent vertices. So here we can have both of these vertices send their packet to vertex C. However, each time step, a vertex can send only one packet over each adjacent edge. So vertex C cannot send both of these to D. The goal is to minimize the time to deliver all packets, where a packet is delivered once it arrives in its destination. So here, with this packet routing, the completion time is 3, and it's optimal in this instance. So, this problem models routing packets in the internet, with the vertices corresponding to routers and the edges to data links. However, a router in the internet cannot know what's going on in a router on the other side of the world. So, what it actually needs to do is decide what to do with packets on it based only on the packets on it, based only on its local view. And this is the routing table problem. In the routing table problem, you are asked to design routing tables for each vertex of the graph that solve the packet routing problem competitively, where a routing table is just a set of local forwarding rules, which tell the vertex which packets to forward over which edges based only on the packets at that vertex at that time. So the decision on which packets to forward cannot depend on packets not at that vertex. And competitively here has just a standard meaning, where the set of routing tables is C competitive if for every packet routing instance of the graph, the forwarding rules have completion time C times the global optimum on that instance. And the goal, of course, is to be as competitive as possible. Alright, so let's work through an example. So here's a graph, and here's a packet routing instance on the graph. We have 4 packets, one from A to E, one from B to E, one from B to F, and one from C to F. And why is the optimal completion time here? Well, it's 3 time steps. We can move the packets like this. Now, let's look at it from the perspective of node B. Suppose that we've designed routing tables for each vertex. And let's take the same instance. So at time 0, node B has 2 packets. It puts everything that it can see into the routing table, which is the current time and the packets at it. And then the routing table tells it what to do. So in this case, the routing table says it should forward the packet B to F to D, and it should just have the packet B to E wait at that vertex. So off it goes. And then next time step again. The vertex has 2 packets at this time step, because this packet A to E arrived in it. But the vertex cannot know that A to E arrived in it. It just sees the 2 packets and the current time. And it plugs that into the table. The table again tells it what to do, and there it goes. And then next time step again, it just plugs this to the table, it learns what to do, and it does that. And eventually all the packets arrive, and this is the completion time for the collection of routing tables on this packet routing instance. In this case, it took 4 time steps, which means this collection of routing tables is at best 4/3 competitive. So, as mentioned before, our result is that for every graph, there exist deterministic polylog and competitive routing tables. Previously, this was only known for randomized routing tables. And for deterministic, let alone polylog, nothing competitive was known. Why would you want to be deterministic? Well, determinism is fantastic. And the problem here with randomized algorithms is that randomness is low. Randomization actually requires specialized hardware, and Routers must be extremely fast. Packets can move at light speed through data links, but a packet waiting at a router for a random generator is moving at 0 meters per second. You don't want that. So the decision on where to send packets must be done extremely fast, and that can be bottlenecked by generating randomness. Also, you really don't want to fail, even if it's unlikely. And if you have a deterministic algorithm, you have absolute guarantees that it's never going to fail. So, I'll give now an overview of the rest of the talk. So far you've seen the problem definition and our result. Next, I'll go over how the problem of constructing competitive routing tables for packet routing can be solved randomly, and why that approach seems inherently random. And then I'll go over how we actually solve the problem deterministically. So, first of all, packet routing can generally be split into two subproblems. And what are these subproblems? Well, let's think about what each vertex has to do each time step. It has to select where to forward each of its packets, and if there are multiple packets it wants to send over some edge, it has to decide which of them it sends over the edge. So this gives rise to two problems, path selection and scheduling, where in path selection we select the path a packet should follow, and in scheduling we resolve conflicts if multiple packets want to cross an edge at the same time. So how are these two subproblems solved using randomization? Well, let's cover scheduling first, because it's the easier one. Now, suppose that each packet already has a path written on it. Of course, packets cannot be modified, but suppose that you somehow have this information. And also suppose that the path set has congestion and dilation, C and D, where the congestion is simply the maximum number of times any edge is used, and the dilation is the length of the longest path for any packet. Now, if we forward packets without having the packets stray from their paths, what is the completion time going to look like? Well, it definitely has to be at least the congestion, and it definitely has to be at least the dilation. Why? Because at most one packet can cross an edge every time step, which means if C packets need to cross an edge, that takes at least C time steps. And also each packet moves at most one vertex each time step. So if the packet needs to traverse a path for length D, that takes at least D time steps. So that's why the completion time has to be at least C and at least D. However, it also turns out that it's possible to have completion time which is asymptotic in C plus D if you solve the problem offline, as in you have all the paths and you see the entire instance and can solve it centrally. And this is a classic result from Leggett, Maggs and Rao. If you want to do it locally, there is also a very simple randomized algorithm using random delays, again from Leggett, Maggs, Rao. So how does this algorithm work? You just sample for each packet a waiting time, which is at most the congestion, and then a packet waits at the start of the problem until its waiting time, and at that point it just starts walking its path without ever stopping. Well, why does this work? Why don't we have packets conflicting? In expectation, how many packets do we have at an edge at a specific time? Because at most C packets use the edge, the number of packets there at any specific time is in expectation at most 1. And that's with high probability, at most log n. So actually, what we can then do is just multiply time by log n. And that gives us completion time C plus D times O log n. Alright, so if each packet has written on it the path that it should follow, and that path set has low congestion and dilation, we know how to solve the problem randomly. But how can we actually select paths for the packets? The problem here is that we cannot select the paths based on the global packet set. We have very limited information what to select the path based on, and basically the only reliable information we have for that is the packet itself. And what does the packet have? It just has a source and destination. Is this enough information to select a path for the packet? Well, it turns out that it is. in the random case. So oblivious path selection is just selecting the path for a packet based on its source and destination by sampling the path from a distribution. For congestion optimization, there is a classic result called oblivious routing, called log and competitive oblivious routing, that says that for any graph, there's a distribution of paths between every pair of vertices, such that if you sample the paths for your packets out of that distribution, the congestion of that set of paths is at most log n times the optimal congestion. However, of course, as we saw in the previous slide, the completion time for scheduling is relative to congestion plus dilation. We also need a guarantee that the paths aren't too long. And in oblivious routing, the paths might be very, very long. So actually what we need to sample from is a very recent result called hop-bounded oblivious routing. This is similar to oblivious routing, except now we have competitive in the completion time instead of just congestion. Alright, so in summary, the randomized approach is to sample for each packet a path based on its source and destination from an hop-bounded oblivious routing, and then run local scheduling by sampling a random delay for a packet, having it wait that long, and then just walk its path. Well, both of these are sampling. Is this inherently random? What do we know deterministically about these two sub-problems? Well, let's look at that. First, deterministic local scheduling. One thing you can note is that any strategy for local scheduling achieves completion time C times D. Why? Because at most C packets want to cross any edge, so you never need to wait more than C time steps to cross an edge, as long as your strategy sends a packet over an edge if no other packet wants to go over it. And also the length of any path is at most D. So basically anything that doesn't just have packets waiting around has completion time C times D. And nothing better is known outside of special cases. So deterministic local scheduling, we just know nothing about. How about oblivious path selection deterministically? So first, what does deterministic oblivious path selection mean? It means that there's a single fixed path between every vertex pair. And this sounds bad, and it indeed is. There's a lower bound of square root n times the optimum congestion on the congestion of deterministically obliviously selected paths. And this counterexample is actually a hypercube. So it's not even some very arbitrary graph topology. These two problems, we just don't know how to solve local scheduling, and oblivious path selection deterministically is probably impossible. Well, are deterministic routing tables doomed then? Well, no. You saw our result. We show the existence of deterministic polylog and competitive routing tables. How do we do it? Well, instead of solving these two problems, we solve these two problems with much longer names. And in fact, a slightly more restricted version of this second problem. So these two pieces here are sparse semi-oblivious path selection from a recent work by Zuzek, Haupler, and Droyskoe, which are actually three of us, Bernhard, me, and Goran. And then also the other piece is local deterministic noise-tolerant scheduling from this paper. The combination is also in this paper, and I'll also go over it in this talk after first describing these two problems. So first, what is sparse semi-oblivious path selection? Well, the core idea here is we cannot obliviously and deterministically select one path for each packet. What if we select multiple? So if we select alpha paths between each vertex pair, well, first of all, what does that even mean? Well, sure, we can select multiple paths for a packet. The guarantee here is that for any set of packets, after looking at these alpha fixed paths for any packet, we can centrally select one path of them for each packet, and then have a path set where the selected paths have congestion and plus dilation at most beta times the optimum. So, a very recent result showed that for any graph there is a polylog and competitive, polylog and sparse, as in there are only polylog paths between every vertex pair, and we can then centrally select one path among those polylog n for each packet to have polylog n times the optimum congestion plus dilation sparse semi-oblivious routing. So this is entirely deterministic. The problem, of course, how do you locally select the correct path? This result essentially only states the existence of the good paths. And if you look at the full path set, as in you would look at all of the alpha paths for every packet, the congestion of this path set might be extremely high. However, this existence of this large subset of paths with low congestion is exactly what we want in our case. And the paths, you can imagine, are hidden among noise, as in the non-selected paths. So that's why we are interested in noise-tolerant scheduling. So consider now that you have a scheduling instance. You have a bunch of packets. Some of the packets you actually care about, and the other packets are noise, but you cannot tell which packets are noise and which packets are the packets you care about. What can we hope for in this case? Well, let P be the path set of the packets, and let S be some subset of the paths. Then we call the subset alpha T good if the subset is both very large, if the subset is not too small, as it's at least an alpha fraction of the entire packet set, and the subset, if only those packets in the subset existed, we could schedule all the packets with low completion time, as in completion time at most t. Then we can hope to run scheduling. So then in noise-tolerant scheduling, our goal given alpha and t is to deliver half of every alpha t good subset. And we can see here that any noise-tolerant scheduling algorithm has to spend at least omega alpha times big T time steps. And why is this? Well, first of all, consider what if alpha is 1. You are delivering half of all packets. So you must have completion time relative to the congestion plus dilation of the packet set, because you can just iterate this log n times. And next, consider what if your subset is just a single packet? Well, then you need to actually deliver all of the packets. But what is the congestion plus dilation of a single packet? Well, the congestion is 1. So the completion time has to have an alpha factor, and it has to have a t factor. And this omega alpha t in general is a necessary trade-off all the way. So now we have this noise-tolerant scheduling problem. We want to deliver half of every good subset in time relative to alpha times t. And one thing you can observe is that this problem is harder than regular scheduling. And for deterministic local scheduling, nothing better than c times d was known. And we actually leave this problem open. We do not solve this problem. We solve noise-tolerant scheduling with a restriction to a poly-sized domain path set. So what this means is that we are given a set of paths, and we are guaranteed that every path a packet has appears in this path set. Or in this case, we call it the domain path set. Why is this not a restriction when combining it with semi-oblivious routing? Well, if you recall semi-oblivious routing, we have alpha paths between each vertex pair, which means in total the number of possible paths is alpha times n squared, which is polynomial. So we can just pass the support of the semi-oblivious routing as the domain path set to our noise-tolerant scheduling algorithm. So, noise-tolerant scheduling given a domain path set. What is our result on this? Our result is that for every graph and polynomial-sized domain path set, there is a local and deterministic noise-tolerant scheduling algorithm that uses only a polylog factor more time steps than is provably necessary, which is extremely good. So now, what we have here is a polylog competitive noise-tolerant scheduling algorithm. And what we had from the previous work is a Polylog sparse, Polylog competitive semi-oblivious routing. Combining these two, we actually get packet routing. Well, how does that work? What is the algorithm? First of all, assume that you have an upper bound big T on the optimal completion time. If you don't have that, well, usually you don't have that, but you can just start with big T equals 1, then double it every time until you are done. So now the algorithm is to first just take an alpha sparse beta competitive semi-oblivious routing for alpha and beta polylog n, which exists by the previous work. Then repeat the following log n times, and the following has the goal of delivering at least half of the packets, so repeating it log n times delivers all of the packets. You iterate over all of the alpha different indices of paths in the semi-oblivious routing, and then for any packet, you set its path to the ith path in the semi-oblivious routing between its source and destination. So yeah, we cannot modify packets. However, the path for a packet in this algorithm only depends on its source, destination, and the current time. So we can just map those 3 parameters to this path in the semi-oblivious routing. This line here isn't an issue. After we have assigned these paths to each packet, we just run 2 alpha t local deterministic noise tolerant scheduling algorithm with return. So with return here means that any packet not delivered returns to its source. It's a very simple extension to the algorithm, easily achievable in the packet routing model. Alright, so why does this route all of the packets? Well, if you look at the good subset of paths guaranteed by semi-oblivious routing, that subset can be scheduled with low completion time, notably with completion time at most big T. And since there are alpha paths between every ST pair, the good subset has size at least 1 over alpha, the total path set. Which means that for at least half of the good paths, they appear for some I where a 2 alpha fraction of the paths for that I are good. And half of those paths and half of packets with those paths get delivered, which means we deliver half of the packets, a fourth of the packets, and repeating this log n times, we deliver all of the packets. Alright, that's it. Thank you.